That one. That's Throwback, the only ogre to ever spit over 3 wheat fields.
Right. Yeah. Hey, can you tell my future from these stars?
Well, the stars don't tell the future, Donkey. They tell stories. Look, there's Bloodnut, the flatulent. You can guess what he's famous for.
All right, now I know you're making this up.
No, look. There he is, and there's the group of hunters running away from his stench.
Man, that ain't nothing but a bunch of little dots.
You know, Donkey, sometimes things are more than they appear.
So, are there any donkeys up there?
Well, there's, Gabby. The small and annoying.
Okay, I see it now. Yeah, the big shining one, right there, right? That one there?
That's the moon.
Oh, okay.
Somebody once told me the world is gonna roll me. I ain't the sharpest tool in the shed. She was looking kind of dumb with her finger and her thumb in the shape of an L on her forehead. Well, the years start coming and they don't stop coming. Fed to the rules and I hit the ground running. Didn't make sense not to live for fun. Your brain gets smart but your head gets dumb. So much to do, so much to see. So what's wrong with taking the back streets? You'll never know if you don't go. You'll never shine if you don't glow. Hey now, you're an all-star. Get your game on, go play. Hey now, you're a rock star. Get the show on, get paid. And all that glitters is gold. Only shooting stars break the mold.
Hello, and welcome to Astronomy on Tap number 71. I am your host, Chaos Cloud, or Rebecca Larson. I am a PhD student at the University of Texas at Austin. My co-host tonight, Dr. Micaela Bagley, Deep Space Shine, is running a little bit late, so she'll be here shortly. So I'm going to go ahead and do this intro on my own for the first time ever. Wish me the best of luck. I'm really glad you guys are all here. This is our 71st show in a row. We do this every month, typically on the third Tuesday. Apologies for the delay this month, but we are here and we are going to have a great show for you tonight. And before we start, I wanted to let everyone know that we're doing something really special for our show in September. We're going to be doing a full Spanish show. We have talks in Spanish, we have the news in Spanish, we have the hosting in Spanish, and we're going to do Astronomía en el Bar on the 22nd of September. And it'll be the same time as normal. It'll be here on YouTube on our page. And so go ahead and tell everybody that we're going to do that. And please come, please watch. We will have a translation subtitles done a few days later. So if you don't speak Spanish, but you still want to watch the show, you still want to hear the talks, we will get those done so that you can watch it with subtitles a few days after it goes live. So please tune in for that show. I'm really excited and really happy that we're able to do this. So we have 3 great talks for you tonight. The first up is our very own MC SuperDuperNova, Dr. Jeffrey Silverman. He's going to talk about death from the skies, or how the universe is trying to kill us. Next up, we have Micalyn Rowe, Darth Astrophysicist, who's going to tell us a lot about Archaeoastronomy, which is also a really cool word and a really cool subject. And third, and definitely not least, we have Ghana Gal, or Jacqueline, who is going to be telling us about behind-the-scenes look at deep near-infrared photometric surveys. So as usual, science is better with beer, so cheers to everyone. We would normally be doing this show at the North Door, an amazing venue here in Austin, Texas. But due to quarantine and being safe, we are doing it here from our homes on the internet. But we still have drinks, so please, special shout out to the North Door for being an amazing host for the past over 5 years now. And another special shout out to the Austin Astronomical Society, who has been our sponsor and has been supporting us since day one. And I also want to give a shout out to Odell Brewing Company for being our official sponsors as well. So if you could help out the North Door during this time, we have their Venmo here. We also still have Pueblo Viejo, the taco place that exists in that venue for us, is still open for orders. So please don't forget to get your tacos like I did today. And every time I forget, but please get some tacos from Pueblo Viejo. They're amazing and they're still open. So go ahead and help them out and help yourself out too. When we are not here live on the internet, you can find the rest of our shows all recorded on our YouTube channel, which you are watching now. So go ahead and subscribe to that. Check out some of the previous talks that we've had and our previous live shows. We have a Facebook page and Facebook group you can follow. We're on Twitter at AoTATX and on Instagram as well. If you have any questions, concerns, thoughts, whatever, please send us an email. This is our email right here. We also have a brand new website. It's aotatx.org. So go ahead and check that out. We're working on putting a lot more stuff on that for you. So go ahead and let us know if there's anything that you'd like for us to see or anything that is missing. And please go ahead there. You can subscribe to our newsletter on the website as well. If you'd like to learn more about Astronomy on Tap as a whole, it is a worldwide endeavor. It's in many different cities all around the world. And so go ahead and check out astronomyontap.org and look at all of the different locations. And many of them are virtual now, so you can attend as many as possible during this time. If you have questions, please go ahead and put them in the YouTube comments as soon as you have them. Our speakers will be giving their amazing talks. And so if you have a question during the talk, go ahead and put that there. We will have people posting those to us so we can ask them once the talk is over. You can also ask questions over Twitter. Use the hashtag AoTATX number 71 and tag us if you can, so that way we can find those questions. If you can reach out to us on other social media, all those kinds of things, please do so as well. We will try to take your questions in whatever way is easiest for you to ask them as possible so that we can get them to the speakers. We are doing trivia. So the trivia link is in the YouTube description, so you can click on that there. We don't have our forms. We're not here in person, so you don't have to write legibly, thankfully. We can just type our answers. And so please, you have the option to sign up for our email list, or you can tell us about yourself or give us some feedback. You can also find any of our previous trivia answers and questions on aotatx.org/trivia. So Micaela did a whole lot of work and made a really great part of our website all about the trivia. We will leave the trivia open. We won't draw winners today so that people who aren't able to watch the show live still have a chance to play. We have amazing coffee mugs that Odell Brewing Company made for us with our really cool logo. They're adorable, and we have shipping stuff and are shipping them out now. So we promise that will happen, and that will happen soon. So please play trivia. You don't have to get all of the questions right to win. We still draw randomly. So just go ahead and play, have fun. All of these questions should be answered during the talk. Please be kind to each other. Be respectful in your comments, in your questions. We are virtual, but this is still a no harassment zone. We will not tolerate that, and we do have people moderating it. Be good humans. It's important to learn and do that together. So without further ado, let us get started. Our first speaker needs no introduction. Jeff, if you could get in here. Jeff is one of the co-founders of Astronomy on Tap Austin. Hey, original t-shirt. We would not be here if not for him and Dr. Rachel Livermore. So I'm very excited to welcome him back. Jeff is now Director of Data Science and Analytics at Samba TV, where he uses big data to, among other things, figure out exactly how many people are watching The Bachelor, which I don't know if I actually want to know. But before moving into the tech industry, Jeffrey was the National Science Foundation Astronomy and Astrophysics postdoctoral fellow at the University of Texas at Austin, and he earned his PhD in astrophysics at the University of California in Berkeley, working on observations of supernovae and dark energy with Professor Alex Filipenko. Jeffrey is a co-founder, like I said, of Astronomy on Tap Austin, and is heavily involved in various science communication and public outreach programs, including co-hosting Big Screen Science, which is a weekly movie showing followed by a presentation via Twitch. And we will get that link to you if you would like to watch that. So Jeff, I'm so happy you're here. Go ahead and take it away.
All right, thanks for that introduction, Rebecca. Here we go. So yeah, it is always great to be back at AoTATX, even virtually from San Francisco. And so I'm going to give this talk today, which is an updated version of the same talk that I gave at it was the first talk ever of Astronomy on Tap Austin on November 18th, 2014 at Easy Tiger on 6th Street in downtown Austin. So a bit under 6 years ago, this thing was started. And this was the first talk out there. So slightly updated, but basically the same stuff. So if you were around 6 years ago, I apologize for the rerun. I don't know what to tell you. All right, and so today I'm going to be talking about death from the skies, or how the universe is out to kill us. This is based on sort of based on a book by Phil Plait, also known as The Bad Astronomer, a really great book that he wrote a few years ago. So the first way, let's jump right into it. The first way the universe is out to get us is with an asteroid or a meteoroid impact. Here we see a map pointing out the Chicxulub crater in the Yucatan Peninsula in Mexico. It's about 110 miles across. For reference, if that asteroid hit UT Austin, the crater would extend almost up to Temple and down past New Braunfels, almost to San Antonio. So a pretty huge area. This crater wasn't an obvious crater. It's partially buried in the Gulf of Mexico, and it's been eroded over millions of years. And so it was only discovered in the late 70s by geophysicists Antonio Camargo and Glenn Penfield. But most scientists now believe that this impact was what started the decline of the dinosaurs, what's known as the KPG boundary. And so evidence that this crater was formed from an impact from space includes various kinds of rocks and minerals that were found nearby, things like shocked quartz, which is in the upper left picture, and that's actually a piece of shocked quartz from the Chicxulub crater. And then in the bottom right corner, those little poopy looking rocks are called tektites. That's another kind of natural glass that's made only in high energy impacts. So when we find that in a place, we can be pretty sure that it came from an impact from space. Another piece of evidence of the impact at Chicxulub is in the form of a gravitational anomaly. And so here is a zoom in on the Chicxulub crater and the Yucatan Peninsula kind of in the shaded darker region, and then the lighter region is the Gulf of Mexico. And you can see where the red and yellow are the sort of strong gravitational anomalies. White are sinkholes. And so you can sort of see that ring of white and yellow, the outer ring on the land, and then that inner ring that's kind of on the land and in the water. And that's, a telltale sign of a major asteroid impact, sort of those two concentric rings. And so from various pieces of evidence, scientists think that the impactor was about 6 miles across and hit about 66 million years ago, give or take 11,000 years. When it did hit, it released about 100 million megatons of TNT, which is about 2 million times more energy than the largest atomic bomb ever detonated. So this was quite the powerful explosion and impact when it happened. So the dinosaurs didn't really have a chance. Moving a little bit northwest of the Yucatan Peninsula, we have Meteor Crater in northern Arizona. So you can go drive by this off a highway and visit it. There's a little visitor center and parking lot sort of just to the north of the crater. You can see that little black bit is the parking lot with a couple of buses in there. So you can kind of see how big this is. It's about 4,000 feet across, almost 600 feet deep. And the rim actually rises 150 feet above the surrounding plains. So the middle got depressed, and then the outer edges of the crater actually peaked up 150 feet above the surrounding area. This was made about 50,000 years ago, so relatively recent as far as geology and astronomy is concerned. And it was by an object only about 160 feet across, and we think it was moving at about 30,000 miles an hour. This one is pretty interesting. The meteorite was mostly vaporized upon impact, so there's actually not much in the crater. It's pretty empty. There's not a big hunk of meteoroid living inside that crater, or meteorite living inside that crater, and so there's really not much there, but still a pretty powerful impact 50,000 years ago. Jumping forward in time, here's an image from near the Tunguska River in Siberia. On June 30th, 1908, a meteoroid exploded in the atmosphere a few miles above this spot. So it didn't hit the ground, didn't really get close to the ground. It exploded a few miles above. And so the object that caused this devastation was probably a few hundred feet across. So it really is the biggest thing to hit the Earth's atmosphere in sort of modern recorded history. Since it blew up so high above the ground, it actually didn't leave a crater like Meteor Crater, but the shock wave from that explosion did flatten about 80 million trees over the span of 830 square miles. So if you were anywhere nearby, that shock wave would have felt like a magnitude 5.0 earthquake. So for all my California friends, we know what that kind of feels like, maybe not so much down in Texas. Luckily, Tunguska in the middle of Siberia was pretty remote, so there was no documented fatalities, but if you had that explosion go off in any kind of city center, it would have leveled, a greater, pretty large area of a major metroplex. I'm sure there were some animal casualties. I'm sure there were some freaked out animals, but no documented human fatalities from that one. Now, jumping to some relatively recent history, just a handful of years ago, February 15th, 2013, a meteoroid that was 66 feet across, traveling 40,000 miles per hour, blew up about 18 miles above Chelyabinsk in southwest Russia. And so when it blew up, and this is some dash cam footage from that happening, it actually instantaneously was brighter than the sun. So people that happened to look that way were temporarily blinded. People felt the heat of the explosion. They reported that later. And as many of you know, light travels faster than sound. So a lot of people, saw this really bright flash, either directly or sort of out of the corner of their eye. They went to the window to look at it and see what the hell it was. And then the sound wave, which is the shock wave, got there later and then shattered the window right into their face. And so almost 1,500 people were injured by the secondary effects of this meteor, such as being knocked down by the shock wave or the window shattering in their face. So if you ever see a bright flash of light outside, do not go to the window to investigate. And so what are some ways that we can avoid this? We've kind of not been doing this for a while, but we have ideas of how we can help mitigate an asteroid or meteor impact. And so one thing that you can do is you can attach a bunch of little rockets to one side of the asteroid before it gets to Earth and kind of just nudge it out of the way. If you catch it really far from Earth, you don't have to nudge it too far because of the way angles work. So you nudge it a little bit and that knocks it off course and we're pretty good. Another idea is you kind of ram something small into the asteroid. You don't have to break it apart. Again, you just kind of got to nudge it. So a space probe, another space rock, something that has, a decent amount of mass, but not monstrous, and just to kind of nudge it out of the way on a different course. Another idea actually is you can shine concentrated sunlight on an asteroid, and that would actually nudge it a little bit. Light, photons that make up light have pressure, they have momentum, and so you can actually use light to nudge it out of the way. This is a pretty slow and weak process, but if we catch an asteroid or meteor early enough, far enough from Earth, this would actually work. And in fact, you can also use what's called a gravity tow, or kind of a little tow truck where you have a really heavy rocket. And that rocket will pull on the asteroid through the force of gravity because everything with mass pulls on each other through the forces of gravity. Newton taught us that a few hundred years ago. And so if you have a really, really heavy rocket that's much heavier than the asteroid, you can kind of use the rocket engines to park it next to the asteroid and slowly move the rocket away. And that'll sort of nudge the asteroid behind it. It'll kind of drag it behind it through the force of gravity. And of course, there's, everyone's favorite idea of just nuking the hell out of it. But that's actually a terrible idea because most of the time when you do that, you just have a bunch of smaller asteroids pretty much still all going the same direction and going to hit Earth. So sorry, Bruce, that is not a good plan. All of these ideas are realistic. They're not science fiction. People have been working on these. They're in various stages of development and testing. But the bottom line is, more work needs to be done. More funding needs to be put towards this. We've seen in Earth's history plenty of huge asteroids that can, take out a good chunk of the Earth or, large city centers. And so the funding and the research needs to go into these kinds of asteroid and meteor avoidance projects so that we can, if we need to, use one of these to nudge something out of the way. And so here's my table of ways to die, ways the universe is trying to kill us. So the first one here, asteroid impact. For a smaller rock, the damage would be local. For a big one like the one in Chicxulub, that could be a global issue. Phil Plait and others have sort of calculated the odds of, an individual death in your own lifetime is about 1 in 700,000. But it's preventable. We can nudge it away. We could blow it up. It's not a great idea, but you could do it. And I do have to mention that in case 2020 wasn't bad enough or weird enough, 2018 VP1 is a near-Earth asteroid. It's about 7 feet in diameter, and it's predicted to make its closest approach to Earth on November 2nd, 2020, the day before the election. Most likely it won't get closer to Earth than the moon, but it is estimated to have a 0.41% chance of hitting the Earth, so not zero. But 7 feet across is actually relatively small, so it shouldn't do any real damage even if it did hit Earth. So maybe we'll be okay. But given 2020, I'm a little skeptical. All right, the next thing we should worry about is our very own sun. So here is the sun as seen from space at about 7 p.m. Texas time. So less than an hour ago, I downloaded this picture from NASA's Solar Dynamics Observatory, which has been up and observing the sun for quite a while, many, many years now. It's relatively calm. You can see some bright spots and dark spots on the sun. You might be able to see some kind of little bright threads sticking out of the sun. And that's basically where the magnetic field of the sun is poking through the surface. And so there's a lot of satellites constantly watching the sun, this one and many others. They're trying to learn about it, and scientists around the world are studying what's known as space weather. Basically, how does the sun act and behave, and how does it potentially affect Earth? And so they use images like this and computer models to predict when the sun's magnetic field will get really twisted up and might have a bit of an outburst. And so here's a movie from that same Solar Dynamics Observatory, the SDO, from about 6 years ago, September of 2014. You have the Earth to scale at the bottom there to show you how big this eruption is off the surface of the Earth. This whole video covers about 2 hours or so. And what we're seeing is hot, high energy particles being blown off the surface of the sun in what's known as a coronal mass ejection, or a CME. Luckily, this one wasn't pointed at Earth, but if it was, we might have some issues. Weaker CMEs and little solar flares can lead to bright and beautiful aurora, what's known as, the northern and southern lights, mostly concentrated near the poles. In 1859, there was a really big coronal mass ejection that led to aurora bright enough that you could read by it at night. Other times when the sun has had these large ejections, there's reports of aurora seen as far south as Florida and Cuba. And so in 1989, there was a large coronal mass ejection that did hit the Earth. And we have an artist's rendition here of the blackout that was seen in parts of Northeast Canada, mostly in Quebec. So the ejected high energy particles and radiation hit the Earth about a day and a half after they ejected from the sun. It overloaded Quebec's electrical grid, and within 2 minutes, millions of people lost electricity for 12 hours. And so while no one will probably die directly from a solar flare or a CME, a coronal mass ejection, ones that are strong enough, like this one that hit Quebec in '89, could severely damage or destroy communication satellites in Earth orbit or electrical grids on the ground. And so once we lose that, we could be in some serious trouble. And so the way to die, solar flares or CMEs, you could have issues with power grid collapse. If it was really strong, you might start worrying about burning off the ozone layer. Again, probably zero chance of really dying directly from a solar flare or a coronal mass ejection, but still pretty bad. They're not preventable, but they're mitigatable. We can build robust power grids. We can build satellites that can go into safe mode. We can observe the sun better and predict when these things are going to go off and protect ourselves, because we do get a little bit of time from when the particles leave the sun to when they hit the Earth. All right, the next way that we're going to die, sharks. All right, so they might be out to get us, but they're not coming from the skies, or are they? I just really wanted to put Sharknado in this talk, so there we go. Sharks, damage, loss of limb, life, obviously potentially needing a bigger boat. Odds are about 1 in 4 million. They're probably preventable, right? I mean, if movies have taught me anything, you can blow them up, you can punch them in the gills. Seems like you could prevent that. Okay, back to some astronomy. So to finish up, a couple more here, potential deaths. So we have the violent deaths of stars known as supernovae, and this is what I worked on. This was my specialty and my PhD thesis topic. And these are some of the biggest explosions in the universe. They can eject material that is expanding at speeds up to 10% the speed of light. In a single month, a stellar explosion like this can give off as much energy as the sun will in its entire 10 billion year lifetime. And so in the bottom left of this picture, we have one single star that's gone supernova in this beautiful spiral galaxy. And so you can see one star getting about as bright as the core of that galaxy. That's about 100 billion stars or so. And here's the famous Crab Nebula in the constellation of Taurus. And so when a star explodes as a supernova, it gives off all this energy, blows this material out, moving very quickly. That material will slam into gas and dust that's sitting between stars, minding its own business, and that'll start glowing and heating up and giving you these beautiful supernova remnants. So that's what the Crab Nebula is, a remnant. And so all the supernova that we've seen in the last few hundred years are stars in other galaxies. So those are way too far away to really affect us. But some ancient supernova that observers on Earth saw well before the invention of the telescope came from stars in our own Milky Way galaxy. And so the Crab remnant came from a star that exploded in the year 1054, seen by Chinese, Japanese, Arab, and Native American astronomers, basically all around the Northern Hemisphere. They noticed it. It was bright enough to see during daylight for 23 days, and it was visible in the night sky for almost 2 years, well before the invention of the telescope. So it was pretty to look at. People noticed it, people wrote about it, but didn't do any damage to Earth. It was too far away, too weak of a supernova. But one star that's going to go supernova soon and could potentially impact Earth a little bit is Betelgeuse, one of my favorite movies, and one of the biggest stars that we know of in our Milky Way galaxy, about 10 to 20 times the mass of the sun. It's a very puffed up star. If you drop it in the middle of the solar system, it would immediately swallow the first few planets. That's how big it is. And so we're not sure exactly when this thing is going to explode as a supernova, probably in the next few thousand years, anywhere between tomorrow and a few thousand years from now. That's the best I can give you, unfortunately. When it goes supernova, it's not going to hurt the Earth. It'll outshine the full moon. You'll be able to read during it by its light. It'll be visible during the day if it's at that time of year. But it's not going to do any damage. People aren't going to die because of it. But we do know in the past, there have been stars close enough that have affected the Earth. In 2004, geologists discovered a weirdly high amount of a special kind of iron called iron 60 in the Pacific Ocean seabed. This isotope's only produced in exploding stars and supernovae, and it was found to be created about 2 million years ago from a supernova that went off only 50 light years away, so about 10 times closer than Betelgeuse. And so we know that supernovae have gone off near the Earth and deposited particles on the Earth, not to mention high energy particles, light, radiation. So definitely people have supposed that some of the major extinctions in Earth's history potentially were caused partially by supernovae. And so, currently we're okay, but in the future, your great-great-great-great-great-great-grandchildren might have some issues. So supernovae, we should be worried about ozone depletion, radiation problems, like that, the evidence from the supernova a couple million years ago. Odds of your actual death per lifetime is about 1 in 10 million, give or take. Preventable, not that we know of. Star's gonna explode, star's gonna explode. Now we can crank it up to 11 with stars exploding and talk about even bigger stars. So this is Eta Carina, a star in the southern hemisphere sky. It's further away than Betelgeuse, about 8,000 light years away, but it's also bigger. It's maybe 100 or 150 times the mass of the sun. This Hubble Space Telescope image is showing these sort of two lobes of gas and dust that were burped off of this star in 1843 when it got very bright and then kind of faded away. And during that eruption, it actually blew off those lobes of material that weigh about 10 times the mass of the sun. So this thing is a huge star. It's been going through death gurgles for tens of thousands of years. It's going to explode as a supernova at the end of its life. But again, sometime in the next few thousand years, we're not really sure when. But this is going to be more than just a supernova. This will probably also have very narrow jets of high energy gamma ray radiation. And these high energy gamma ray beams will cause it to become what's known as a gamma ray burst, or a GRB. These are basically cosmic blowtorches. You have a regular supernova with a blowtorch of gamma rays coming out each end of it. Luckily, we're not looking down the barrel of the blowtorch. You can kind of see the lobes are kind of at an angle to our view from Earth, which is good. But if there's any planetary system that's looking straight onto those lobes, they should be a little bit worried. And so gamma ray bursts are even more powerful than supernovae if you're looking down the barrel of the blowtorch. Again, concerned about ozone depletion, radiation, potentially setting the entire planet on fire. These are concerns, but they're more rare than supernova. So maybe 1 in 14 million chance. And again, star's gonna explode, star's gonna explode. There's not much that you can do about it. And so looking over this chart to kind of sum up where we're at, seems like maybe we should be worried about asteroids in the sun, maybe sharks, but we have ways of preventing asteroid strikes, and we can certainly lessen the effects of the CMEs and solar flares. And so, research has been slow, mostly to levels of funding to find asteroids, to test ways that we can nudge asteroids out of the way. And so, that's something that definitely could use more funding and more research. I'll point out that the odds of you being killed in a terrorist attack in the US is about 1 in 30 million. And we spend a hell of a lot of money on protecting us against that each year. So maybe take a little bit of that and think about asteroids or solar flares. All right, probably don't need to worry about supernovae or GRBs killing you. One last thing that I'll mention is the odds of winning the jackpot in the Texas lottery, about 1 in 25 million. So they're even off the charts here. So don't play the lottery and fund asteroid avoidance. And with that, I'll finish up. Thank you very much. Rebecca mentioned this at the beginning, so a shameless plug for an event that I do every Wednesday. I'm happy to answer more questions about this, and we'll share the link around. But we watch a science movie or any kind of movie and talk about the science afterwards. A good friend of mine, Kishore, and I. Tomorrow's night's movie will be Ocean's 11, so 7 p.m. Pacific, 5 p.m. Central at the Twitch site. And with that, thank you very much.
Thanks, Jeff, and thanks for giving me lots of other things to be concerned about, especially in this wonderful 2020. So excited. So can you just real fast, you mentioned your big screen science. Is there a movie that you did that you really wanted to talk about the science of, or the lack of science therein, that you would suggest people start with? Was there a favorite episode of your show?
So yeah, we've been doing the virtual ones and they're all on that Twitch page. We did WALL-E, which is, I'm a huge Disney fan. It's my favorite Pixar movie. That has a lot of really, really good science, as many of you probably know. So Wally was a really fun one. That's a really good one. Let's see. There's a lot of good ones on there. We hope to eventually do Groundhog Day again. We did that live in the Alamo Draft House in San Francisco, and there is a surprisingly large amount of science in Groundhog Day. Astronomy and data science. Maybe we did it. I think we did do it on the virtual one, so it should be on the Twitch page. I can't remember all the ones we've done, but yeah.
Well, even if you've done it, you got to do it again, right?
Yeah. There is a weirdly large amount of science. It's a very fun one. I believe it's on the Twitch page, so go ahead and check that out.
Perfect. Okay, I will definitely be doing that. All right, so we have a question for you from Alan. How do we test one of these nudging options for asteroids? Is real-time practical experiment necessary, or we can rely on simulation to try to figure that out?
Yeah, that's a great question. A lot of the work, as you might have guessed, is sort of simulation, computer simulation stuff at this point. So that's part of it. The other aspect of it that's gotten some funding, but certainly needs more, is just looking for the asteroids that could potentially be an issue and tracking those. But as far as like testing some of the technology, like in flight in space, the US and various other countries have sent probes and satellites to comets and asteroids, with a couple landing, scooping up material, stuff like that. And so we have the technology to get spacecraft to asteroids and comets. And then it's a matter of, sending those out there and doing the test and seeing, can we nudge something into a slightly different orbit? You hope you don't do it wrong and nudge it from a safe orbit to an unsafe orbit, but
or
you
blow
can
it up
probably
into more pieces.
So right. You can probably do the test, hopefully in a safe way. But yeah, you would really want to actually send it to an orbit, an asteroid in the asteroid belt, or an asteroid that's maybe Earth crossing or near Earth, but on a pretty far away, safe trajectory, and nudge it and see how that actually works in space.
Yeah. Well, that would be very interesting and exciting, and I can't wait till we're actually out there moving bodies in the solar system. We have another question. Can you discuss a little bit more how you know that Betelgeuse will go supernova in the range of 1 to 1,000 years?
Yeah, so there's a number of people, many based at UT Austin, that are experts in the world on this exact topic. So I certainly don't want to speak for all of them, but I can give a little bit of background. So we know that massive stars, things like Betelgeuse, that are 10 to 20 times the mass of the sun, they don't live very long. And not very long in astronomy star terms is sort of tens of millions of years. We can estimate the age of the star from the way it looks, from the chemical composition, from how big it is, from how hot it is, things like that. And so we can sort of get an age estimate of the star. We can get a pretty good mass estimate of the star. And we have a pretty good relationship between mass and age and how long it takes for a star to kind of run out of fuel and die. And so you put those all sort of together and you get that it's pretty close to the end of its life. Now, pretty close on, a 10 million year lifetime is, a few thousand years is the last little percentage of the lifetime. And so, it really does seem to be anywhere between tomorrow, when it's going to explode, and 1,000 to maybe 10,000 years from now. That seems to be the ballpark number. Professor Craig Wheeler at UT and some of his students over the years could give you, I'm sure, extremely precise numbers and much deeper explanations on that.
Yeah, it did kind of give off a big stink and have everyone really excited recently when it dimmed. But no explosion yet.
keep looking.
Guess we'll just have to wait. I wanted to ask you just a quick question for anybody who might be interested. So you did your undergrad degree and you did a PhD in astronomy, but now you work in data science. Can you talk a little bit about how those two things are related?
Yeah, sure. Yeah. So not only did I get a PhD, I did a postdoc, which is what brought me out to Austin after that. And then, made the transition from academia to the tech industry. And a lot of the skills translate pretty directly. Instead of looking at thousands of exploding stars, I'm looking at thousands of smart TVs around the world and what people are watching, millions of smart TVs now. So, dealing with big data, being able to write clean computer code, a fundamental understanding of statistics and probability, those are all sort of key things that I learned in my academic career that I use day to day. And, to be totally honest, the other huge skill that is crucial to my job and that I get, positive feedback about pretty often is communication skills. and being able to describe and talk about a very technical topic at a variety of levels to a very non-technical crowd or a very technical crowd. And astronomers tend to be really good at that because we have really cool stuff to talk about to the public and they're interested. And we have events like Astronomy on Tap and Pine of Science and Nerd Night and all these things. So I credit, a lot of these kinds of events with making, a lot of astronomers and physicists I know very good communicators, science communicators, and that's directly translatable to the tech industry.
That's awesome. I think that's hugely important. And thank you again for making Astronomy on Tap in Austin a thing that happens every month for 71 months now. I think it's been an incredible experience, and I'm really glad that you were able to come back, well, virtually come back. But thank you, Jeff. We will have more questions for you at the end. So if there was a question that you had that didn't get asked, please go ahead and continue to put those in the comments, and we'll call Jeff back after the end of the show with the rest of our speakers, and we can ask the rest of those. So thanks, Jeff.
Thank you.
All right, so next up we have Micah, and Darth Astrophysicist. She is going to be talking about archaeoastronomy. So Micah, come on over. She was born and raised Texan. She's half Filipina and half white. She has a bachelor's of science in mathematics and physics with a minor in astronomy from Texas A&M University Commerce. She loves to read books, spend time outdoors with her human partner, and Beans, her dog, watch interesting TV, photograph special moments, travel, and expand her horizons. She believes that the world is a better place when people act selflessly, which is so true. And she is currently a second-year graduate student at Texas A&M University, down the street from us. Her past undergraduate research experience consists of some mathematics, which is specifically complex analysis, some acoustics in designing a recording studio, and a little bit of astronomy in carbon atmospheres of white dwarf stars. She's currently working with Peter Brown and Nick Sunseth for her graduate research, and she's looking at the ultraviolet optical telescope GRISM spectra of type 2 supernovae. So we have another supernova person. She's going to talk about some really interesting stuff, so go ahead and take it away.
Thank you so much for introducing me. Let me get this pulled up. And can everybody see everything okay? We're good? Okay. And sorry for my dog in the background. So good evening, you guys. First, I would like to just thank our friends here in Austin for letting me share my talk with y'all tonight. My name is Micalyn Rowe. Like Rebecca said, I'm a second-year PhD graduate student at Texas A&M University in College Station, and tonight I will be talking to y'all about something called archaeoastronomy. Now, what is archaeoastronomy? Archaeoastronomy is the investigation of the astronomical knowledge of prehistoric cultures. This is a really cool subject. Just a little advertising. This is an amazing class that's offered at Texas A&M University Commerce, where I did my undergrad, and you get to travel to different sites and actually see the history that you learn about in class. And so a little bit about what I'm going to be sharing with y'all today is going to be pictures and also information about some of the different historical sites around the globe that have some type of connection to astronomy that we can really obviously see. And so to get us started, this is a picture in the background of the slide of Casa Rinconada, which is in Chaco Canyon. And this is a structure in New Mexico. I actually got to travel here with my class at A&M Commerce, and I will be talking more about this site later on, so kind of look out for it. So the first big thing that I wanted to talk about is Stonehenge, which is located in the United Kingdom. It was built around 3000 to 2400 BCE, and these stones actually had a certain structure to them. The outermost circle of stones is going to be called the Sarsen circle. And then you can kind of see this inner horseshoe of stones is called the trilithions. And then at the bottom of the U shape of the horseshoe is a stone that we call the altar stone. And yeah, so it's inside the horseshoe of stones. And you can't see them in this picture, but there are these little holes in the ground called Aubrey holes. And now they are filled with chalk, but weirdly enough, they used to be filled with cremated remains. And so the last important structure that I wanted to mention here is the heel stone. It's located in the upper right-hand corner, but it's not in this current picture's view, and we'll see it in just a second. And we'll be able to see how it specially aligns in the next slide. So like I said, there's a significant astronomical alignment that happens with this heel stone. If you were able to go out to Stonehenge on the summer solstice sunrise, and if you could stand at the altar stone and look towards the heel stone, you could see the sun rise right over the heel stone, as you can see in the picture. And vice versa, this also aligns on the sunset of the winter solstice. And solstice alignments are actually, with ancient cultures, are pretty common throughout history. So another cool thing about Stonehenge is that this structure isn't alone. There's another place that we like to call Woodhenge. It's located in the United Kingdom, still around Durrington Walls, and I'll show a map in just a second for reference. Unfortunately, this wooden structure didn't preserve as well as the stones, and we only know about this because of excavated remains. So here's a map of the area for reference. Stonehenge, you can see, is almost here in the center. Woodhenge and Stonehenge are connected by this thing called Stonehenge Avenue, and then you can move along the Avon River, and then you can move up Durrington Avenue, and you can finally reach Durrington Walls. Durrington Walls is just a big circular trench, and this is actually where Woodhenge would have been located. And there's also this weird feature called the cursus. It's literally just a big rectangle carved out of the ground. And so now we move to a location that's a little bit north or west to Ireland, to a site called Newgrange. This is a burial mound that was built around 3100 BCE. And here, lined up in the front, you can see these stones called curbstones. And these are elaborately curved stones with spirals on them. And here on the left is an up-close look at a curbstone. And on the right, you will be able to see different points of view of the inside of the burial mound. So here on the top is a top view. It is a tunnel shaped like a cross, and this cross points southeast to line up with the winter solstice sunrise. And like I said, this is a burial mound, so the bodies were kept in the wings of the cross. On the bottom is a side view of the mound, and you can see this little structure that has an arrow pointing to it on the right. This is called the roof box. This is actually the little window that allowed light from the winter solstice sunrise to reach the back of the tunnel and illuminate the back wall. And then also, as you can kind of see, the tunnel slopes up so that the sunrise can reach the back. Next, we're going to move a little southeast to the Egyptian pyramids. Fun fact, all of the pyramids are actually on the west side of the Nile. This is because the west side in Egyptian culture represented death because the sun sets in the west. So they first used these things called mastabas, which are underground burial chambers to bury their dead. And then they eventually started to move to above ground burials. Shown here in this picture are the Great Pyramids of Giza. Again, the entire reason for these pyramids was to get the pharaohs to the afterlife. And their attention to detail for these things were insanely precise. For example, they used a cornerstone on the southeast corner of the pyramid to line up the rest of the pyramid with the cardinal directions. Again, they only used one stone to line up the entire pyramid. It's pretty awesome and pretty accurate. And so they built some cool astronomical alignments into the structure of their pyramids. This is actually a mock-up of the interior of the Great Pyramid of Khufu. It was built in 2554 BCE, and the entrance is on the north side. The most interesting thing about this, like I said, is the astronomical alignments, and we're going to be looking at the air shafts. So the bottom left air shaft points to a star called Sirius, which we know today as the brightest star in the sky, and we also know it as the Eye of the Dog, aka the Eye of Canis Major. The top left air shaft points to Orion's belt. Orion's belt is a series of 3 stars within the constellation of Orion, and Orion's a pretty well-known constellation. The top right air shaft points to Thuban, which at that time was their North Star. And this is also known as Alpha Draconis, which I just thought was a cool name. And last but not least, the bottom right air shaft points to Kochab, which is the brightest star in the bowl of the Little Dipper, which we also know as Ursa Minor. Moving even farther east, we can look at Polynesian wayfinders. Yes, this is like the people from the movie Moana. The Polynesians would sail great distances and would navigate the Pacific Ocean from Hawaii to Fiji. Their navigation techniques were the stars, currents, waves, and they also used birds. A specific technique that they used was to deliberately sail east of an island, and then once they reached the correct latitude, they would travel straight west until they hit the island. And how they knew their latitude is they would use their hand in relation to the constellations and stars in the sky. Now we move farther east and we finally hit some of America's sites. This is Chaco Canyon in New Mexico, like I mentioned in the beginning. I actually got to travel here and see these sites with my class in commerce. This area was inhabited by the Anasazi people, and this name was actually given to them by Native Americans, and it means ancient ones. Their structures were built in about 950 to 1150 AD. And specifically, this picture is a picture of Whata Butte. And I want you to remember this structure in just a second. So first, we're going to look at a structure called Pueblo Bonito. A special astronomical alignment with this is something called the meridian wall. You can kind of see it splitting the structure. And this wall lines up straight north to south. These circular dips that you can see in the ground are called kivas, and they were big circular rooms underground that were covered with wood. They would use these as a gathering place. The wood that they used to build the different levels is actually how we dated these structures. And something else that was kind of cool is that they actually made very short doors. When we walked through this site, people would bonk their heads all the time. And then when they left, they would brick in these doorways. And we don't know why they bricked the doorways in. The next site that we can look at is Casa Rinconada. This is a picture on the very first slide. And this is also known as the house with no corner. This is known as one of the great kivas. This was actually a decent distance away from Pueblo Bonito, which was the structure we just looked at. And you can see these 4 holes here in the bottom of the pit are for wooden posts that were used to hold up the roof. And then around the side, you can kind of see the dark little spots. Those were the niches in the walls for the roof joists. Now, something cool about this structure is that on the summer solstice sunrise, there was a window in kind of the top right edge of the house here that would let the light shine through into the structure. And like I said, we were going to revisit this. This is actually a picture of the side of that Whata Butte that we looked at the beginning of this series of slides. And what is special about this is that different events with the alignment of the sun and the earth actually cause different light slits on this spiral. And so on the summer solstice, this light dagger is placed in the center of the spiral, and you can kind of see it here on the left. And then on both the spring or fall equinox, the light dagger falls in the center of the smaller spiral, as you can see here on the left. And then on the winter solstice, there are some light daggers that hit on the outside edges of the big spiral. And how they managed to create these light daggers is they leaned these huge slabs of stone up against the side of Whata Butte, and with those alignments, somehow they knew that they lined it up to where on these special events, the light would come through and line itself up on the spiral nicely. And one last thing that we got to look at here in Chaco Canyon was something called the SuperNova petroglyph. This was a petrocarved hiero painting that was preserved beautifully because it's actually on the underside of a ceiling that's sticking out of the cliff face. So things like erosion and weathering couldn't get to it and destroy the painting. We think that it depicts the July of 1054 AD supernova that Chinese astronomers actually were able to see and recorded. And that's why we actually have such a specific date for the supernova. And what this event was, is it's when the Crab Nebula blew up. So the next thing I wanted to talk about was this site called Teotihuacan in Mexico. This was built around 100 BC, and it means City of the Gods. This place actually predates the Aztecs, and as you can as you can see, there are two pyramids here, and the road isn't actually straight north to south. This road is called the Avenue of the Dead, and then the orientation of the pyramid is wonky to me. The pyramid of the sun is beside the road, and the pyramid of the moon is at the end of the road, which for me, that should be switched. So the north side of the sun pyramid lines up with the sunrise on February 9th and November 2nd, and the sunset on April 30th and August 13th. So another site in Mexico that we can look at is Tenochtitlan. This is built in 1325 AD. It's located on Lake Texcoco, where the Aztecs built this. And their beliefs said that they should build a city where they saw an eagle eating a snake on a cactus, which is super specific if you ask me. And if they did this, then they would be a great empire. And as you can see, these structures were very organized. All the roads were lined up with the cardinal directions. Here's another picture or a mock-up of their plaza. The blue temple is the temple of Tlaloc, which is the god of rain and fertility. And the red temple is the temple of Huitzilopochtli, which is the god of sun and war. And this whole big structure, both the blue and red temple together, is called Temple Mayor. And so from this viewing platform, which you can kind of see as like a circular pyramid here in the center, on each of the equinoxes, if you stood on that, then you would actually see the sun rise directly between the blue and the red temples. And the last site that we're going to kind of visit is called Machu Picchu, which is in Peru. This was created by the Inca. It was used 1438 to 1472, which it wasn't in use that long. It was used as a summer palace for Emperor Pachacuti. And so one building in particular is interesting. We call this the Torion. And there's a window that casts this shadow here in the center, this window on the left. And this actually points towards the rising of the Pleiades. And then the window here on the right, you can almost see it above the edge of the wall there. It points to the rising of Kolka, which is the last two stars on the tail of Scorpio. And this last picture, this is actually the homes in Mesa Verde in Colorado. This is the second site that I got to visit with my class. They had really cool dwellings that would be nestled underneath cliff faces to protect them from the weather. And with that, my presentation has come to an end. I would like to show my references for the pictures quickly. And remember that you can put any questions that you have in the YouTube chat. Thank you so much for listening to my talk, and thank you, Austin AOT, for having me.
Thank you, Micah. That was really, really exciting and really interesting. Not only did I learn a ton, but I'm super excited that we got to hear about archaeoastronomy, since I feel like most people don't know that that's a thing. So can you tell us a little bit about some of the places that you went to and which was your favorite and probably the most surprising thing that you learned while you were actually there?
So my favorite definitely had to be Chaco Canyon, because there were just so many sites like crammed into one, geographical site. And like I said, there were like 4 places that we got to visit. I will say, I mean, it's good because it got me moving and got me walking and stuff, but we had to hike a lot. We had to climb up the cliff face so we could see Pueblo Bonito from the top down. But yeah, Chaco Canyon was definitely my favorite. It's a great place to go hiking away from light pollution. If you want to bring a telescope out there and look at stuff, they have camping available and everything. So it was really cool.
I will add that to my list. All right, so we have a question from Brad. Do you know what the oldest stone circle in the world is and when it dates back to?
I don't.
I don't know what the answer is.
Yeah, I honestly don't. I mean, there are, Stonehenge is pretty old, but I don't know if that's the earliest, because maybe we haven't uncovered the earliest thing yet.
True, it could be still buried somewhere. Are there any rituals associated with astronomical events that you are aware of?
Yes. There were rituals that they would hold on the solstice. Sometimes it would be, a day celebrating life. But usually on the winter solstice would be like an event celebrating death. It just depended on the culture, honestly, and like the significance that these sites and these astronomical alignments held in their culture. So.
Cool. I think that there's a lot of things that we have to like learn from like old text and stuff like that. Like you said, the supernova, we know it happened because of like the things that they wrote down back then, and I think that that's really cool that there's a significant importance to astronomy like throughout all of human history, and it's pretty cool to be a part of that in a way. Okay, so one last question from Alan. Are there larger seasonal astronomical cycles that render Stonehenge slightly off kilter for a time, where, for example, the heel at Stonehenge isn't right on point for a decade or a century or something like that?
I'm not entirely sure, but I'm gonna say no, because the sun pretty much stays on the ecliptic pretty regularly, and in our lifetime, precession isn't going to mess us up with that much, or mess up our alignment with the sun that much. So I'm gonna say no for our intensive purposes and our time periods.
Right. It's definitely not something that's going to happen on the order of a month and then go back or something like that. I think it would be over a longer period of time, like you said. Awesome. Well, thank you so much. That was such a great talk. We did steal Micah from our friends over at Astronomy on Tap in Bryan College Station with the A&M people. So she gave a talk last week, I believe. So check out their show. We'll make sure that we put the link in the comments and in the YouTube description for you. They have a lot of really cool stuff going on as well. And so next up is everyone's favorite part of the show. We have our dynamic duo who are going to give us astronomy in the news. Danny and Jackie, will you please get in here and make this happen?
Hello. Well, we'll do our best.
We're missing Jackie.
Howdy.
All right. Awesome.
Welcome to Astronomy in the News. Let's get this going. Yeah.
You're doing great.
I got this.
Hello, everyone. Unfortunately, we have to begin news with some tragic news rather than happy discovery time. So in the early morning hours of August 10th, a mysterious tragedy occurred in Puerto Rico. At Arecibo Observatory, a steel cable weighing in at 13,000 pounds snapped without warning, ripping a huge gash in the 307-meter radio dish. In its epic descent, the cable apparently thrashed around wildly. I imagine it's something like Shrek's dragon when she gets trapped by her neck in the chandelier and is trying to fly, and the chain keeps flapping. And I wrote that joke before I knew what our intro video was going to be, so I feel like I'm on the same wavelength with our Astronomy on Tap staff here. So with that striking visual, you can imagine the damage it caused to the Gregorian dome, which is the suspended structure above the dish that holds a bunch of the detector's instruments, as well as the primary reflector, which is the mesh that you're seeing on the ground, where it tore 30 meters of the fine mesh. So in some parts of the world, we talk about building a 30-meter telescope, but I guess the universe instead heard, let's destroy 30 meters of telescope, which kind of seems like a cosmic middle finger, but it's okay. So back in the before times, Arecibo laid the foundations for radio astronomy back in the early 1960s. At the time it was built, it was the largest single aperture telescope, And that record was only beaten in 2016 with the completion of the 500-meter aperture spherical telescope, or FAST, in China. It has an impressive resume when it comes to discoveries in the radio sky, including the first direct image of an asteroid and the first observations of binary pulsars and neutron stars. It was also used during the Cold War to locate Soviet radar satellites by detecting signals that bounced off the moon. So most importantly, though, it also enjoyed quite the stardom as a character in things like Contact, GoldenEye, and even the X-Files. But what makes Arecibo particularly unique is not its receivers, but its transmitters. It is the only radio telescope capable of sending signals into space. The most notable use of this feature was in the transmission of the Arecibo message in 1974 by Cornell astronomers Frank Drake and Carl Sagan, which signaled our first real attempt to contact the aliens of Messier 13, which is 25,000 light years away, so you'd think it would take a while to get a response back. Rumor has it that the original draft of Hotline Bling said, "You used to call me on your frequency modulated radio waves, but it didn't really rhyme with love." Wait, that's the wrong Drake. Ramon Lugo, who is the director of the Florida Space Institute at the University of Central Florida, which operates Arecibo, simply called the situation concerning and said cables don't usually break like that. So they've been saying lots of things in 2020 don't happen like that. No one is really sure what caused the break. Repairs were completed after Hurricane Maria caused some damage in 2017, and Tropical Storm Isaias seemed to pass it by with no problem. And there were no other storms in the area. Spokespeople gave a feeble explanation of like maybe there was seismic activity, even though there was no other damage in the area reported. And observations have been halted for at least the next 2 weeks, although the observatory is unsure how long repairs could take, with estimates ranging from a couple of weeks to the end of this year. So is it any coincidence that our main landline to extraterrestrial intelligence was suddenly severed in the middle of a global apocalypse at 3 a.m., which is the devil's hour, no less? I think not. Personally, I think the aliens might be mad at us. Maybe they hated Drake and Sagan's message. But most of all, let us pray for whoever that overnight operator was, because as Danny and I can tell you, that unexpected rain, randomly forgetting what's coming up in the sky at the moment, and just plain falling asleep can result in some awkward phone calls from the operator. So I can't imagine what I would have done if a cable suddenly snapped the telescope in half. So anyway, hopefully Arecibo will be okay soon.
Yeah, this definitely makes me feel a lot better about some of the mishaps also I've had while observing. I also don't know what I thought that the like dish was made out of at Arecibo, but I didn't think it could just like be kind of ripped like a t-shirt. Like,
yeah, it really can. Well, the cable was 13,000 pounds, so that's a thick cable.
Okay, that explains that. Oh, poor Arecibo. So this month, I bring you an icy moon adjacent story, I might call it, an icy dwarf planet story about the dwarf planet Ceres. And yes, this story does mean that dwarf planets can be interesting. And yes, that includes Pluto. And yes, its demotion did not make it any less interesting than it was before. Sorry, I'm talking about dwarf planets. I can't resist a little bit of a Pluto rant, but back to our spotlight object of Ceres. Ceres is the largest object in the solar system's asteroid belt. It's actually the first asteroid that was ever discovered by Giuseppe Piazza in 1801.
Can you get a more Italian name than that? Hello, my name is Joseph Pizza.
I was gonna say if it was Giuseppe Pizza, then maybe. It was Ceres was reclassified in 2006 as a dwarf planet when Pluto was reclassified, and they came up with this dwarf planet status, right? Because it is quite different than the bulk of the asteroid belt. It's much bigger. It's much more massive. This one object contains 25% of the entire mass in the asteroid belt. And it's also, as you can say, spherical, right? Most asteroids are not large enough to become spherical. So Ceres is pretty interesting, right? We've known about it for a long time, and it's a really large object in the asteroid belt, but because it's an asteroid and they're kind of hard to observe, we didn't really know too much about Ceres for a while. But eventually it had been observed that there were these weird bright regions on the surface of this dwarf planet, but we didn't quite know what they were. All we really knew was that they probably had to be young regions. They had to be relatively young because Ceres is constantly impacted by micrometeorites. And so that would darken the surface of the dwarf planet over time. So these must be relatively new, fresh surface on the dwarf planet. So here we enter NASA's Dawn mission, which is a satellite that was sent to the asteroid belt. It's actually the first satellite ever to orbit two different celestial objects. First, the large asteroid Vesta, and then Ceres. It reached Ceres in 2015. Its prime mission lasted for about a year, but again, because of these bright regions and because of Ceres's status as a dwarf planet, its mission was actually extended for 2 more years, over which it actually has now figured out the mystery of these bright regions on the dwarf planet's surface. So the satellite, in its orbit around Ceres, got as close as just 20 miles above the surface, taking unprecedented images of the dwarf planet. And what they actually discovered was that these bright spots were sodium compounds. Sodium, salty. If you've ever heard me talk about the icy moons, you know that their subsurface oceans are quite salty. And so the idea is that these compounds are brought to the surface by subsurface water. So that's really exciting. But again, subsurface water doesn't necessarily mean subsurface ocean. There could just be some ice around, and when, say, a micrometeorite hits, it heats up the surface, melts it, and bam, there is your salty material. But if that were the case, again, these things wouldn't last long. So there has to be replenishment of this liquid salty water. And so as Dawn orbited the dwarf planet, it was actually able to map out Ceres's gravity and figure out its internal structure. And what they found was that where they were finding these bright regions, they discovered a reservoir of brine about 25 miles deep, which is 4 times deeper than the deepest ocean trench on the Earth. And it stretched for hundreds of miles across the dwarf planet. So while impacts do bring up some of this salty water, the key is that the crust fractures, and then this reservoir of salty, briny water can come to the surface, right? Maybe one day we'll be able to harvest some of that brine and eat truly out of this world pickles. Now, this is different than the icy moons that I love so much, mostly because why does Ceres have liquid water in its interior, right? It needs to be heated. Those icy moons have tidal heating. They're stretched from gravitational interactions, and that heats the interiors and keeps their subsurface oceans liquid. But there's no tidal heating on Ceres, and it's a pretty small object, so you would expect most of its heat from formation to have dissipated by now. But its crust is actually very insulating, and not all of its water on the interior is liquid, so it has just enough heat to keep some of its water liquid in an ocean. So this isn't quite the ideal environment that you would expect for life, or the ideal environment for life that I have ranted about on Europa or Enceladus many times over, but it could be. And regardless, it really tells us that these subsurface liquid water oceans on icy worlds are probably quite common. And so again, we'll have to wait. We'll probably never know if life exists in the interior of Ceres, but just in case, Dawn was actually decommissioned into a long duration orbit around the dwarf planet so that it won't impact and potentially contaminate it with any Earth life or materials that have remained on the surface of the satellite.
Well, that's really cool. But I was distracted by you saying brine multiple times, and so I think I will just call you Captain Ahab now. I was like, what does brine mean?
The Ceres pickles, so.
I would love an interplanetary pickle. So now we have the mysterious case of the missing neutron star. So a fool might say, that the most important events of 1987 were the release of Bruce Springsteen's Tunnel of Love, or the debut of The Simpsons, or the inaugural opening of Starbucks. But who could forget the arrival of Supernova 1987A? Not me, because I was born yesterday, cosmically speaking. But Supernova 1987A went off on February 23rd in 87. Yes, that's how we name these things. And it is located in the Large Magellanic Cloud, which is 51 kiloparsecs, or more sensibly, about 168,000 light years from Earth. So that's how long ago it went off, but it took that long for us to see it. It's the closest observed supernova since Kepler's supernova was visible back in 1604. And that's what they really mean, what they're supposed to mean when they say something is a once-in-a-lifetime opportunity. I'm sparing you from yet another Talking Heads joke because I've made it for like 3 months in a row now, but what I mean by that is that we really need to stop calling things unprecedented when new apocalyptic things keep happening every day. But anyway, back to the supernova. The brightness peaked, the brightness of the outer explosion at least, peaked in May of that year. And ever since then, it has served as an amazing laboratory for investigating core collapse supernovae at basically every single wavelength. Core collapse supernovae are a special type, and I don't ever get the types correct. So I couldn't really tell you the other kinds. This is basically what a supernova means to me, is that you have a massive star, in this case, a blue supergiant, and it burps off its outer layers in a really violent supernova explosion that travels outwards for a pretty long time, while the inner remnant collapses either into a black hole or a neutron star. And the boundary of where that happens is based on some other initial conditions of the star. So by observing the supernova later, you can learn about the evolution of the star itself. So neutrino observations around the time of the explosion suggested that a compact object did form at the core, but evidence of the core itself has eluded astronomers ever since that fateful 1987 day. The Hubble Space Telescope started taking images of the supernova remnant starting in August of 1990, but to no avail, leading some scientists to conclude that the supernova remnant was a black hole. If you are a member of the Carl Sagan Club, if you catch my drift, you might even think that it turned into a quark star, which is not a thing that's ever been confirmed. But if you really have a galaxy brain, you could think it was a quark star. But a third possibility is that it's a neutron star, which is already intrinsically dim, but it's hiding behind a thick cloud of dusty debris that would have been blown out during the original supernova, which would still be visible since the supernova is not that old. In a paper published in the Astrophysical Journal about 6 months ago, Dr. Phil Segan of Cardiff University led a study of supernova 1987A using ALMA, which incidentally has not recently been the victim of a falling cable attack. So it's fully functional. And at 870 microns, a hot blob was sitting right in the center of the old explosion. So that's the orange fiery thing you're seeing in the figure there. And the chemical composition, which was mostly excited carbon monoxide and signatures of large dust grains, supported this dusty shroud theory. And then in a landmark theoretical paper led by Dr. Denis Page of UNAM in Mexico, new results from supernova modeling further supports this theory of a young neutron star. So by modeling the stellar evolution just before the explosion and then the subsequent pathways of the ejecta, they were able to predict what kind of object it would leave behind and what kind of observational features it might have. So the model showed how the shock of the supernova could kick away the neutron star from its birthplace, so that the remnant would not be found exactly where the original star was, and it gets shot out with a speed of a couple hundred kilometers per second, which is about 10 times faster than any rocket we've ever launched from Earth.
Does that not count as a yeet?
Oh, that's a yeet. That's totally a yeet. I can't believe I missed this clear opportunity for a supernova shock to yeet a star away.
Talk about unprecedented. I create.
You're so right. I have egg on the proverbial face. The temperature models predicted a staggering 5 million degrees Celsius, which should be very bright at sub-millimeter wavelengths. So the only scenario which matched the observations was in fact a dusty neutron star. So it lacked the magnetic field signature that would have indicated that it was a pulsar, which if you recall is a spinning neutron star, I think, right? Don't ad lib when you don't know. I think it's a neutron star and it rotates really fast and it's got a magnetic field. And 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 the dust observation was too bright to come from a black hole, because obviously if it was a black hole, it would be black. But even the small amount of material around the edge of it would be below any detection limit. So definitely not a black hole. And they concluded that they had discovered a 25-kilometer wide neutron star. I tried to calculate a reference for 25 kilometers, but I honestly don't know what a kilometer is. So it's just like a small town, I guess. So born only 33 years ago, this is the youngest neutron star that we know of in the nearby universe. And with all these neutron star discoveries, I hope you have been convinced that alt radio telescopes reign supreme over every other wavelength. And that's true even when the cosmic Big Rip destroyed one of them, because it's still the best one in the game. And that's that for the radio sky.
I'll stick with my optical observations and not needing to pretend to know how Fourier transforms work. So, if you're like me, you might remember earlier this year, Betelgeuse dimming in the sky. If you're also like me, that might feel like it was a decade ago, but it was not. But anyway, Betelgeuse was in fact dimming from late last year through early this year, reaching a minimum in February, being about 3 times fainter than usual, which is, I guess I'll use the word unprecedented, before brightening again and going back to its typical, or close to its typical brightness. Now, while the star was dimming and when it would reach that minimum, there was questions about, what exactly was happening. Was it about to go supernova, which some of us were kind of hoping for? Was light just being blocked by some dust? Was there just weird star stuff going on with convection cells and everything, and that it'll just go back to normal? Well, we have an answer. This is not a new answer, but it's from a new study led by Andrea Dupree of the Harvard Smithsonian Center for Astrophysics. And they used the Hubble Space Telescope to answer this question. And it turns out, I believe we talked about this possibility in a news story earlier this year, but that the star was just being blocked by a big cloud of dust that it actually created itself. So the team used Hubble to take ultraviolet spectra of Betelgeuse. And because they were looking in the ultraviolet, it probes the very hot outer layers of the star above the visible stellar surface. Now, these outer layers can be affected by what's going on the interior of the star. So they were able to kind of use that as a probe to see what was going on. And beyond that, they were actually able to spatially resolve the spectrum. So basically, they could say, what does the spectrum look like at different latitudes on Betelgeuse? And these observations are actually a part of a 3-year study, so not necessarily directly tied to the dimming event, to monitor variations of this star. So not only did they have this spatially resolved spectra, but they also had spectra over time, allowing them to see what was going on before, during, and after this dimming event. And so what they found was that in late 2019, part of the star looked really hot, and that there was this really hot, dense material moving at 200,000 miles per hour out of the star's surface and crashing into its outer atmosphere, which they were able to observe. Now, at this point, Betelgeuse looked normal in the sky because, again, our eyes can't see ultraviolet. But eventually, that material got far enough away from Betelgeuse that it cooled down enough to form dust. And then that dust proceeds to block some of the starlight. So actually, once it became dust, the UV observations went back to normal. So it actually reached normal UV brightness before it reached normal optical brightness. So as you can see in this image on the screen, Betelgeuse burps out this material, and this dust cloud aligns along our line of sight to block out part of the starlight. So I guess even Betelgeuse is imploring us all to wear face coverings. So mystery solved, mostly. Interestingly, NASA's Solar Terrestrial Relations Observatory, or STEREO, gotta get an acronym in, has been observing the star and actually saw it dim a little bit again this summer. Now, not nearly as much as it was earlier this year, and we will need to continue observations this fall, but perhaps Betelgeuse will continue to be doing something interesting as it teases us with its eventual supernova light show end. Cool.
Awesome. I like that dusty Betelgeuse kind of looks like those like snappy piranha things from Mario. Do you know what I'm talking about? Do you know what those things are called when you're playing Mario Kart and then like the Venus flytrap things like eat you?
Oh, piranha plant?
Yeah, I think that's what's happening here.
Oh, okay.
In my scientific opinion.
Yes. We live in a universe that is just a simulation written by Nintendo. That checks out.
Absolutely.
The world would be a much better place. Cool. Well, that's the news for August. Oh. Wow, I'm really incapable of zooming anymore.
I can't believe a new semester is about to begin and I have to relearn how to use technology.
Yeah, I will probably continue to fail at Zoom every time.
Thanks, everyone.
Bye.
Thank you, Jackie and Danny. Thank you so much for doing the news. Hi, everybody. Thank you also to Rebecca for covering for me while I was late to this show. Next up, I would like to invite Jacqueline to join me here with, please turn your video on and join us. It is my absolute pleasure to introduce Jacqueline. Rebecca and I have the honor of working as part of her, well, so we're in sort of collaborative research groups. We get to work together quite often, and we're very, very lucky to get to work with her. Jacqueline is a rising fourth-year PhD student at Texas A&M University. Her research involves using novel infrared instrumentation to search for massive quiescent galaxies at high redshifts, which she's going to tell us a little bit about today. And I do have to say that if of all of the people I've been observing with, and I've been on many observing trips, Jacqueline is the most fun to observe with at 2 a.m. in the morning when you're starting to lose it and you just need a good friend to observe with. So she's great. So please take it away, Jacqueline. We're excited for your talk.
Thank you very much, Micaela. Let's see if this works with Zoom. Okay, so hopefully you can all see my screen. Cool. So this image here is the Hubble Deep Field, taken in 1995 and released in 1996. It's considered to be one of the images that revolutionized modern astronomy. For 10 days, Hubble stared at this small region of the sky located above the Big Dipper constellation, which you see here, and imaged it in 4 different wavelengths of light, spanning the optical to the near infrared. And this region is actually very small. How tiny, you say? We're talking about the size of a pinhead at arm's length. That's how tiny this region is. And in this small region of the sky, Hubble was able to capture almost 3,000 galaxies. You can see them here in the Hubble Deep Field image. They have different sizes, colors, there are different stages in their evolution, and there are different distances. So Hubble gave us this view of what the universe looks like at different epochs, all the way to the very early stages in the universe. And so this picture is revolutionary because we were given in a single picture over 10 billion years of cosmic history. And this birthed a new era of deep imaging surveys, which we now use to look for these distant galaxies. And that's what I'll be talking about today. So I'll touch a bit on some of the science we can do with these deep imaging surveys, and also touch a bit on some of the less glamorous, but just as important parts of making these beautiful images that you saw. So This is the Hubble Ultra Deep Field, which was released in 2004 as a successor to the Hubble Deep Field. It took about 800 exposures over the course of 11 and a half days to take this image. And you can see the wonderful diversity of galaxies again here. This is a galaxy that is very much like our own, the Milky Way. And we're seeing it as it was about 5 billion years ago. And so the wonderful thing about this picture is that you're actually looking back in time. What we really have here is a three-dimensional view of the universe. And as we go a little bit farther back, we come across this galaxy that's about 9 billion years, actually these two galaxies, and they look like they're interacting with each other. And these two galaxies are what come together to form some of these elliptical galaxies that we see in the nearby universe today. And if we go even further back, all the way back to about 12.6 billion years in time, this is when the universe was a baby, less than 8% of its age, we see this little red galaxy here, which doesn't look like any of the galaxies that we've seen so far. These are some of the farthest galaxies that can be observed in optical light. So to see any farther, you'd actually have to go into the infrared. And that's because as the universe expands, the light from these really distant galaxies is stretched out in the fabric of space-time. And so the more distant the object, the more stretched out its light is. And for some of these very distant objects, the light is so stretched out that it moves completely out of the visible and into the infrared. And so they can only be seen in infrared. Some of these galaxies are also obscured by dust. And unlike visible light, infrared light, which has longer wavelengths, can actually peer through that dust and give us a glimpse of what some of these distant, possibly dust-obscured galaxies could look like. So astronomers typically observe in 3 regions of the infrared: the near infrared, the mid-infrared, and the far infrared. And each region tells you something slightly different about what the universe is doing at various epochs. So in 2009, the Hubble team installed a new near-infrared camera on Hubble and used it to image the Hubble Deep Field. This is the 2004 image that we saw before. And although the quality of the infrared image isn't quite the same, it's not as good as the optical image, you can see that it revealed a whole new world of galaxies, these distant red galaxies that we saw before. And if you actually blink the 2 images, you can see what I'm talking about here. These galaxies pop in and out of view as you shuffle between the optical and the infrared. So the infrared really does unearth a whole new world of galaxies that are beyond the visible, beyond what you can see with just the optical capabilities. Some of these galaxies were formed about 13 billion years ago when the universe was just 6% of its age. I think that's really remarkable. So let's go back to that really red distant galaxy we saw in the video, in the Hubble Ultra Deep Field image. You may have noticed that this galaxy is so unlike any of the other galaxies that we saw before, like the beautiful spiral Milky Way-like galaxy that we saw, or the interacting ones we saw. It's unlike any of them. And that's what makes some of these distant galaxies so interesting to study. By studying them, we can actually learn something new about what the universe was doing at that young age. They are very, very red. Over the past decade, due to data that we've taken from ground-based telescopes, we've actually got to learn a bit about some of these really distant red galaxies. We know, for instance, that they have these extreme properties. So although they're about the same mass as our own galaxy, they start off with these extreme star formation rates. So they are forming stars at up to 1,000 solar masses per year. So that's astronomers speak for 1,000 suns per year. And just for comparison, our own galaxy only forms about 1 to 2 suns per year. So that's a lot. In addition to this extreme star formation, they quench their star formation very rapidly. So they stop forming stars abruptly, and then they just evolve passively. So they are made up of these really old stars, and that's what gives them this red color that you see here. So what's the best way to study these galaxies? One of the great things about the Hubble Space Telescope is the fact that it's in space. So you don't have a lot of the obscuration from the atmosphere that you get in the ultraviolet and in the far infrared, which is great. But unfortunately, Hubble is only optimized to observe a very small sliver of the near infrared. And so to detect, and remember, to detect these really distant galaxies, we need deep observations spanning hundreds of observations in the near infrared. Also, the other thing is exposure time is inversely proportional to the size of your telescope. And so the bigger your telescope is, the less time it will take to achieve a certain depth. Which means that the James Webb Space Telescope is actually really ideal to detect these really distant galaxies because it's much bigger than the Hubble Space Telescope. So this is the size of the primary mirror for JWST. This is a human here to scale. And it's also going to be in space, which is great. So we don't have the atmosphere blocking out the light like we saw in the previous image. But the problem is it's not going to be launched till next year, fingers crossed, we're all hoping. But in the meantime, we have these large ground-based telescopes, so 4-meter class and 8-meter class telescopes that we can use to conduct these observations and take these really deep images to observe these distant galaxies. There are only a handful of these in the world, and fun fact, most of them are actually built after Hubble, which I thought was really interesting, in line with Hubble, unearthing this new era of photometric surveys and all of that. So this is a telescope that I actually used for my thesis work. It's the Gemini South, it's the 8.1 meter telescope at the Gemini South Observatory in Chile. So it's quite large, as you can see here, compared to the James Webb Space Telescope, for instance. So how do we look for these distant red galaxies using these deep near-infrared photometric surveys? We use these large telescopes to survey large areas of the sky. And this allows us to get an accurate count of these galaxies and study them in a statistically meaningful way. This is an image showing some of the surveys where we have deep pre-existing data from Hubble and other ground-based surveys. And you can see here that since the Hubble Ultra Deep Field, which I showed a couple of slides ago, we've imaged progressively larger areas. This allows us to, again, make an accurate census of these galaxies and try to cover as much of the sky as possible. So you can see here, this is one of the legacy fields that has been observed, Cosmos. It's actually 16 times the size of the moon. The moon is here for scale. So what actually goes on behind the scenes in these deep near-infrared photometric surveys? How do we produce these beautiful images that we saw before? What's the process? Let's take a look at a single pointing from the telescope that I'm using, which I showed before. This is what a raw image from the telescope looks like. And it's such a far cry from the beautiful images I showed before. And there's one reason for this. The reason for this is the near-infrared astronomers' arch enemy, the sky. The sky is incredibly bright in the near-infrared. It's about 10,000 times brighter than our science targets. And it's, for me, really annoying because I'm the grad student who has to sit down and do all the work. But unfortunately, we can't remove the atmosphere, even though that would be great. So what we do instead is we come up with really clever ways of eliminating the atmosphere from the images so that we can actually see these distant galaxies and then start to study them. So how do we go from that crappy raw image to this beautiful image over here containing over 600 galaxies? What we do is we take several short exposures at each pointing. So there are actually hundreds of exposures that go into each pointing, but I'm only showing a few of them here. These are a few of the raw images taken by the 8.1 meter telescope at Gemini South. And why do we take so many of them instead of just one long exposure? The reason for this is because the sky varies so much over a very short time scale. So the only way to accurately track the variability of the sky is to take short exposures at regular intervals. And that allows you to accurately determine what the sky is doing, how it's varying, and then subtract it from your images. The other thing that we do is something called dithering. So we take the images, but then shift them slightly relative to each other. And that allows us to accurately track, again, both the variability of the sky and get as much of it as possible so that we can subtract it from the images. So this GIF here is just showing all the images that I showed before, but then because they're slightly shifted relative to each other, you can see them jumping up and down. So how do we do the sky subtraction? We actually do it in two passes. For the first pass, what we do is for every single image, we take the first 4 images before that image, and then the next 4 images after the image, and then do a running median. Once you get an estimate of the sky using the running median, then you subtract it from each frame. So these are showing the individual sky subtracted images. So just shuffling back and forth, this is the before and this is the after. So you can start to see some objects start to show up because we've done the sky subtraction. So if we do a zoom in of one of them, again, you can start to see some stars, some really, really bright objects showing up. So it's getting better, but we're not quite there yet. There's still a long way to go before we can produce those beautiful images. So you might be wondering, what is this really ugly thing at the bottom of our near-infrared images? The tricky thing about observing in the near-infrared is everything glows at those wavelengths. Even your telescope glows at those wavelengths. So over here, this is actually the wavefront sensor of the telescope, and it's glowing. So it's this really bright thermal source in our images. So the next step in the data reduction or the sky subtraction is to mask the wavefront sensor or any other artifacts, any telescope optics that might be in the way, in addition to your sources, to get a better handle on the sky and simply just to remove them because they're ugly and they really shouldn't be there. So like I mentioned, you mask these sources and then you repeat the whole process again. So take the first 4 images from before, take the last 4 images behind that image that you're interested in, take the running median, and then you subtract. And this is what it looks like once you've done all of that. So you can see that in these frames, the wavefront sensor from the telescope that we saw before is no longer there. Hooray. You can also see that the image actually looks slightly deeper. That's because now we were able to do better sky subtraction. So you see more objects start to show up. But we're not quite there yet. The final step is to take all of these lovely individual sky subtracted images and then inspect them for their quality. So you look at how bright the sky is, in the residual sky that is in every single image. You investigate the image quality. So what's the seeing like in each image? And then you weight all the images based on your assessment. Once you do that, you can do a weighted sum to produce the image that you see here on the right. So this is a composite image of all those hundreds of exposures again, but I'm only showing a few here. Hundreds of images that go into this image you see here on the right, showing these really, really deep observations. Some of these galaxies are starting to show up here. Unlike the Hubble deep field image that we saw, it's not color, it's not false colored, so it's grayscale. But this is the process that goes on in producing these really, really beautiful near-infrared images that you see. So the whole process that I just described is just for one pointing, one of our Gemini pointings that goes into this huge mosaic you see here. And we have, I don't know, like 80 or so pointings, that's the green circle I'm showing here, that go into this single mosaic. So my job so far has been to do that for all those pointings, which we then combine to make this huge mosaic that you see here. So just to summarize, yeah, these deep near-infrared surveys are our window into the early universe. Even though they are relatively recent, we've had quite a few advances in instrumentation and a few advances in the discovery of these really distant red galaxies that are so intriguing to study. And so I'll leave you all here with this nugget from XKCD. While we wait for James Webb, these large ground-based telescopes are all we have. So hopefully James Webb will be launched soon, and then we can do even more exciting science with the telescope. But until then, we have these deep near-infrared photometric surveys. So I'll end here and then take any questions.
Awesome. Thank you, Jacqueline, so much for that amazing talk. That was awesome. We do have a few questions here. So first, I'm wondering if you can talk a little bit more. So you described what the process is in terms of what sort of things you have to remove from images that are taken with these telescopes. What are the techniques that you use to do that? What are the tools you're using to remove the sky and the other features you mentioned?
Right, that's a really good question. So the techniques, so everything I just described was actually a summary of, I don't know, 10-ish papers spanning, I don't know, however many years. And there isn't, say, like one software that all the near infrared people use. Everybody has their own custom written pipeline, custom written package. And the pipelines have, you know, all these different steps that you have to do that I just summarized. So yeah, to answer your question, the software that we use is custom written. So we have to write our own code to do the sky subtraction, to do the image combination, to do the weighting. Yeah, I think that should answer the question. Yeah.
That sounds like a lot of work. Right.
Yeah.
I think you're making it seem easier than it is. I think you're, but that's okay, cool. All right, so another question here. So in the final mosaic that you showed from Gemini, the mosaic itself looked like, it was sort of rectangles, but the telescope mirror is a circle, and the images that you showed were circles. So how do you go from the circular individual images to the rectangular mosaic?
Yeah, that's a really good question. So the mosaic I showed isn't the composite mosaic from Gemini. Sorry, I should have been more specific. That's the composite image from a previously existing survey from which telescope? It's the Cosmos survey, right? So the Gemini pointings, once we're actually done with our mosaic, it'll have a slightly different look. So maybe I should go back to that particular image so I can give a better description. Right, so I'm showing the Cosmos mosaic as a backdrop, showing what our final mosaic would kind of look like once it's done. So our pointings, like you mentioned, are circular. And so once our final mosaic is done, it's not going to look like, you know, these stripes that you see over here. It'll have a slightly different look, but this is just showing the area in particular that we are observing at and the area that we're covering.
Okay, cool. We can't actually, I don't think we can see your screen fully, but I assume you're referring to your last slide there, or the second to last slide.
Oh yeah, you can see my screen.
We can see, so we can just see the top bar, but not the image that you're trying to show.
Oh my God. Zoom things.
Oh, there it is. There we go. We can see it now. Okay. Yes.
Okay. Yes. So again, this is just a backdrop showing, hey, this is the area of the sky that we observed, but this isn't the mosaic that we made. The Gemini mosaics would look very different, not very different, but because the field of view is a circle, like the person who asked the question pointed out, you won't have these sharp edges that you see here once we're done with our mosaic. But this is just showing our pointing against the backdrop of this mosaic to show the area that we're observing.
Okay, great. Thank you. Okay, so we've got time for one more question from Alan, referring to the galaxies that you're studying with infrared light and in these images. So Alan asks, did the earliest galaxies form in clusters also? And were the clusters as dense as later galaxy formation clusters?
That's actually one of the questions that we want to probe. Because, I mean, so the short answer to that question is, if you look at cosmological simulations to try and see how to make one of these fuzzy red distant galaxies, none of them actually has the recipe right for making these galaxies. So are they formed in clusters? Are they formed from mergers? How come you have a really massive galaxy at those epochs? Because again, the universe is just 6% of its age. How do you even have enough time to form something that's that massive? So yeah, those are all really good questions that we're hoping to answer with, again, better images, hopefully spectra in the future. And then once James Webb comes along, we'll know what exactly, how do you make, you know, these really distant red galaxies?
Yeah, you're pushing the frontier of this field with your observations, trying to push into all the questions we don't know. We can't predict. This is the same as the galaxies that I study at much greater distances. We have no idea how you form so many so early. So, you know, you have to take the observations to start to inform the theoretical models. Like, you know, a sort of cooperative approach to answering this question. Very cool.
Exactly. Yeah. You have this feedback loop. Yeah.
Nice. Yeah. Awesome. Well, thank you very much for your talk. If you're able to stick around, Rebecca and I are going to do sort of close out the show briefly, and then we'll bring all of our speakers back to answer a few last questions. So thank you again. That was awesome.
Thanks, Jacqueline. That was awesome. Always good to hear about the science that we do too. All right, so let's do this.
First, I feel like I should ask Rebecca, how drunk are you after that JWST talk?
No comment. I made the mistake of switching to bourbon before she started, so we're good. It's fine. Let's do the thing. Okay, so yep, go ahead.
Okay, so thank you for joining us for this show. Just jumping right in, if you are playing our trivia game, we will announce, as we have been doing for the last virtual shows, our trivia answers and winners at a later date. So if you are watching this show not live, but in the next couple of days, we'll keep the trivia form open until Friday evening. And that's when we'll close the form, submit the answers to our website, and announce or email the people who have won. Remember, you do not have to get everything right to win. So you can still be playing even after the show's over. And if you want to check out our trivia questions and answers, they will be available on our website probably this weekend when I get to it. But after Friday.
We're doing really good. Everything is completely on time and great. Yes. So again, a big thanks to the North Door, our venue where we would normally be at. I also want to give a short shout out to Easy Tiger and some of the other places that we did start this Astronomy on Tap. So Jeff mentioned before when he gave that talk, our first Astronomy on Tap in Austin was at Easy Tiger, another bar here locally. But North Door has been our home for many years. So please give them your patronage when we open back up, and check out Pueblo Viejo for tacos when you're hungry. Another shout out and thank you to our speakers tonight, to all of our space cadets. So there's a lot of people behind the scene that make this show work, and to our AoTATX committee. We couldn't do this without you. There's a big group of us. Thank you to everyone who is moderating the comments. I believe Sam and Drea are in there right now and making sure that we get the questions. We really appreciate all of your hard work. But most of all, thank you to you guys, the audience, for watching the show, for encouraging us to do this every month, and for always being so very enthusiastic. You make all of this worth it.
As Rebecca mentioned, of course, AoTX
every time.
Everything's fine without our awesome venue. So please consider supporting the North Door through their Venmo, which we have up on the slide and in the YouTube description. They're not able to open, they're not able to have crowds. They've lost a lot of revenue during this time. So please consider giving them what you would have given your bartenders in tips or otherwise during a live show. And also don't forget that Pueblo Viejo and all of their amazingly delicious tacos are still available and open for online ordering and pickup. So don't forget to submit your orders for your Pueblo Viejo tacos on their website, which we've listed on the slide.
We also have both of those links in the YouTube description, so you can just click on them if you can do that. I mentioned this earlier. Our next show in September is going to be the fourth Tuesday.
New time.
What is time? Okay, it's going to be the fourth Tuesday of September, so the 22nd of September, and we're going to do the full show in Spanish. And I'm very excited that we're able to do that. We have three speakers. We have an Astronomy in the News segment, and we have two new co-hosts for you. The whole thing, like I said earlier, will be in Spanish. And Micaela and I will try to say hello at the beginning. See how that goes. And then we'll hand it off to some other co-hosts to do the whole thing. Did you want to say anything else about this, since I kind of already did that earlier?
Yeah, I'm sure you mentioned it. For anyone who missed it, we are incredibly excited about this show. It will all be in Spanish, as Rebecca mentioned. We will have English subtitles available in the video a couple of days after it posts. So if you don't know Spanish, but you want to still check out the show, you will be able to, just maybe not live. But I still recommend, letting your friends know and joining in. And even if you don't understand everything, you'll still be able to experience an awesome science and astronomy show, which, you know, is what we're all here for. So we're incredibly excited about this show. We're excited to invite new co-hosts and all of the new speakers. And we hope that you will join us and tell all your friends about it for the 22nd of September.
Yes, cannot wait. And we're gonna brush up on our Spanish intro.
Yes.
Until then, check us out when you get a chance. We have more videos here on YouTube, so you can subscribe to the channel and check out any of our previous talks. We're also on Facebook if you would like to follow us there. We post our events as well. We're on Twitter and Instagram at AoTATX. Send us an email if you have a question, or if you have a suggestion for a talk that you'd really want to hear, or something for a future show. Our brand new website, Micaela has put a ton of work into, and it looks amazing, is aotatx.org, so please check that out. And if you're interested in Astronomy on Tap or any other kind of astronomy shows that might be more physically located closer to you, astronomyontap.org is where you should go. It is worldwide, and we have many people from all over the world doing things like this all of the time. Many shows are virtual, so you should be able to find other videos if you're interested in watching those. And if you're interested in another Astronomy on Tap show, check out all of the channels that this channel subscribes to. Those are all the rest of the Astronomy on Tap shows that are virtual at the moment. So you can have more space in your space.
That's nice. I like it.
I just thought of it. Okay, so that is the end of our show, but I believe we still have some more questions for our speakers. So could everybody please come back? Cool, hello. Hello. All right, so if you still have questions for the speakers that were not answered during the talk, or you just have questions about anything else, please go ahead and put those in the chat or tag us or wherever, and we will start asking those questions. So for Alan, who's asking us right now, the third Tuesday is still our planned and dedicated time slot. I just failed this month, and then next month we wanted to be courteous of a holiday, so we moved it to the fourth Tuesday. But after that, it'll go back to being the third Tuesday.
But what a plus of virtual life.
I know, right? Right. And so, okay, so we have a question for Jeff from your talk. Is there any kind of planet that could disrupt the equilibrium of the orbits of the planets as they are right now in the solar system that could cause some chaos here?
I mean, nothing that we know of right now. There's some observations that have, we've talked about, I know we've talked about at Astronomy on Tap Austin about Planet 9, potentially some Earth or maybe Neptune-sized object well beyond the orbit of Pluto. There's some evidence for it. I haven't heard too many updates lately. Maybe some of the other folks have heard updates on where those observations are at. But, that's a pretty big thing that is barely detectable in its influence on other objects. And so nothing that we know of that would really, shake things up too much or, send stuff flying towards the Earth that we should be worried about. Early in the life of the solar system, when the sun and the planets were first born, there was a lot of that, a lot of interactions of the planets, the early planets, the protoplanets, flinging stuff every which way. And so that definitely was happening early on, but things settled in the solar system as it was forming after, a billion-ish years, probably less than that even. And so, yeah, things are pretty stable in the solar system as they have been for a few billion years.
It's definitely reassuring and good to know that we don't have to worry about anything.
One fewer thing to worry about, I guess.
That part of the universe isn't going to kill us. Right. Micah, we had another question for you from somebody named Aubrey. What are the Aubrey holes at Stonehenge?
The Aubrey holes are just like, they're literally just these like little holes in the ground that are now filled with chalk. But yeah, they used to be filled with like cremated remains. We don't know why they're there. They're just there. At least it's chalk now though. So
why is it chalk?
Why is it chalk?
Mm-hmm.
I don't know. Maybe to be less creepy, or maybe so people wouldn't like take stuff. I don't know.
All right.
I have a question for Jacqueline. You mentioned, sorry, one sec, reading it. Okay, you mentioned a lot of telescopes in your talk. If you could design your perfect telescope, what would it be and why? Big question. We could ask everybody.
We all know what Jackie's gonna say.
Or James Webb or what? I mean, I certainly would design it so it doesn't take 3 decades to launch, for one.
That hurt a little bit.
Sorry. Honestly, that's a really hard question. I think so at least with the types of objects I'm interested in, the main thing is we want something that can observe in the infrared. We want something that won't have, this huge blocking of light from the atmosphere. So ideally you want something that would be in space, and then something that can observe in the infrared. But James Webb already meets all those criteria, with the exception of the launch date and all that. The only thing I really wish James Webb has, or James Webb would have, which it doesn't have, is the ability to be self-service like Hubble. But then that's impossible because it's going to be all the way out in L2, which is like 1 million miles from Earth or something like that. So anyway, I guess, to answer your question, my perfect telescope would be James Webb, but then serviceable. Although I don't think that'll be possible. So
Well, thank you for making me drink more of this bourbon. For anybody who doesn't know why I keep drinking, every time somebody mentions James Webb, it makes me really nervous because I'm very concerned about this telescope working. So we started a drinking game for solely myself, apparently, during this show, and it gets dangerous.
People rise to it.
Well, it's true.
Hey, Rebecca, do you want to drink even more? So I found out that apparently people had been planning for James Webb since like 2007 or something, and they were saying that in 2010 or so it would launch, and here we are.
That XKCD comic is so accurate. It's very, but it's going to happen. It's going to happen.
Maybe when we're postdocs, professors.
Yeah, well, it's no longer my PhD, but here we are. New subject. Okay, so Jeff, is our sun too small to go supernova? And how do we arrive at the chances for death by supernova?
Yeah, so there's sort of 2 main ways for a star to go supernova. One that I sort of mentioned in the talk, you have to be kind of massive. So about 8 times the mass of the sun or bigger. So our sun is not more than 8 times the mass of itself, so it won't go supernova that way. The other main way to go supernova is if you have a binary companion star. Our sun is a single star. That's its life decision, and we're comfortable with that, and we support that decision. But the sun, most stars, maybe probably more than half stars, have a binary companion. If you have sort of a moderate-sized sun-like star that has a companion, at the end of its life, it can actually steal material from that companion and then eventually get too heavy and explode. So our sun definitely will not go supernova, but we can identify stellar systems in our sort of galactic neighborhood that will go supernova. Things like what I talked about and what was mentioned in Astronomy in the News. Betelgeuse is a massive star, maybe 10 or 20 times the mass of the sun. It will go supernova. That really massive star, Eta Carina, that I mentioned. And so we can sort of look around us and say, okay, how many of these massive stars are nearby? How powerful would such a supernova be from something that massive versus, how far away is it? Because if it's really far away, it's not going to affect us too much. Eta Carina is very massive, but it's pretty far away. And so by looking at sort of the stars nearby, how massive they are, how far away they are, estimating how much energy would come out of the supernova, and then, how much energy would be deposited on Earth, and sort of, through modeling and simulations, what that kind of effect would be. That's sort of how people, including Phil Plait, the author of this book, and others have calculated those sort of odds of, the Earth getting hit by a supernova or an individual dying by supernova.
An individual dying by supernova and not everyone would be a very surprising happenstance.
Well, you do the ratio of divide the probability by the number of people, and the math works out to death per person per supernova. There's a talk about units from Astronomy on Tap Austin that I'm going to watch later because I didn't know about that one, but that's a great one. So yeah, you can cover all kinds of fun units in astronomy.
That's true. Is there a star close enough to us that if it went supernova, we would have a problem? I mean, obviously the sun, but it's not going to. So
Yeah, so what's really useful or good about the very massive stars, the ones that are going to explode that are sort of 8 times the mass of the sun or bigger, they're really big, so they're really bright. So we actually know of pretty much all those big massive stars in our neighborhood. We know how big they are and we know how far away they are. So none of those are going to hurt us. You know, and we also kind of have a pretty good idea of if any of them are going to go gamma ray burst, go GRB with that blowtorch of gamma rays. There's a couple that are sort of a little scarily close, but they really don't appear to be pointing at us. And so that high energy gamma ray energy, when it goes off, won't hit Earth. So we'll be pretty good from there. The stars that steal material and explode as a supernova, they tend to be very small, relatively faint stars called white dwarfs. They are kind of hard to spot because they're not very bright. But we have, people have looked for those nearby, and there doesn't seem to be too many likely candidates of white dwarfs that have a binary partner that can steal material that will go supernova. It's still a fairly rare occurrence in the Milky Way galaxy. And so we should be pretty good. There might be a white dwarf hiding kind of nearby that we just haven't found yet, but it's pretty unlikely.
That's reassuring, and that's good to know. So less things the universe is doing to kill us.
Sure.
I'll take it.
Less is more. I have a question for Micah. How has what you've learned through studying the ancient cultures changed your approach, understanding, or experience of astronomy in your other classes and your research?
Wow, that's an awesome question. Honestly, I mean, I feel like it hasn't affected my research very much because I kind of study supernova like Jeff right now. But in the way that I approach astronomy in general, it really just gives me an appreciation, especially for like looking forward into the future when hopefully I get to stay in academia teaching my future classes. Just like really giving like a historical context. Like we're not the first people to look at the stars. We've always looked at the stars. And it also actually helps us like identify some like misconceptions that we can have about astronomy also. And I don't know, it's a really cool subject, and it gives me some good travel plans for the future also. So
nice. Well, we hope you stay in academia so you can teach us all those classes soon.
All right, Dawn, I don't know if I want to ask this question.
You do.
Do I? I don't. When do we start placing bets on first light of JWST versus the Giant Magellan Telescope? Does anyone want to explain what the Giant Magellan Telescope is? Do I? Okay, all right. So it is a big telescope that is being built in Chile right now. The University of Texas at Austin is actually like 10% ownership partner in it. And it was scheduled to be built and done in like 2025. It is now pushed back to like 2029 because some of the parts were a little bit more complicated than we expected them to be. So it's a set of like a lot of really big mirrors. And so it'll be a really big ground-based telescope that will have high resolution because the light gathering power, the size of the bucket, the mirror itself that gathers all that light is super, super big. And so it's going to be like one of the largest telescopes in the world. And there's several of them at these like 30-meter like class telescopes that are being built. And it will be able to do some of the science that we can do with like the Hubble Space Telescope, but on like Jacqueline showed that there was like a field of view the size like slightly bigger than the moon. You can actually see more of the sky all at once. And so it is being built right now. We've broken ground on it and it's getting put together. Several of the mirrors are already completed versus the James Webb Space Telescope, which was supposed to launch who knows how long ago anymore, and is fully built and under like testing phases and things like that, and is scheduled to launch next year. We've been saying that for 5 years. Probably more than that, you're right. So I don't know, Dawn. I want it to be the James Webb Space Telescope. I really do. But I honestly wouldn't be surprised if it was the other one. That one at least doesn't have to get launched to space. So there's one step that is a big step that isn't necessary for the Giant Magellan Telescope versus the James Webb Space Telescope. So, Jeff, we have another question. What are the odds of a shark-like comet we don't know about coming at us out of the deep to wipe us out?
I mean, in the next few months, based on 2020, high, sure, why not? That seems reasonable enough. I mean, there's been, there's the comet that's going to, or the asteroid that's going to come close to Earth on the day before Election Day. There's been a weird spike in some shark attacks off the New England coast. Like, why not? I mean, maybe there'll also be murder hornets because that's also a thing this year.
What even happened to that? That was like
I mean,
big thing.
Well, right. That's where we're at in 2020 is murder hornets were like low on the list of like news stories, right? Like that's terrifying and ridiculous all at the same time.
Yeah. Well, who's surprised? I don't know how, like, statistically, I'm not like really familiar with it, but how likely we are to detect comets early. There's a lot of things out there that are very faint and they move, and it's very hard for us to constantly watch every single spot in the sky all of the time. And so it is likely that we will miss things as they move through our solar system, since they're very, very small and they don't emit their own light. So it's hard for us to see them. But as far as like a comet that's going to be close to us, that's just going to show up out of nowhere with no warning, I don't know that is very likely. And if it is, then what are you going to do?
I mean, so there are, groups around the world that are doing just this, that are looking for near-Earth asteroids and things like that. One of the biggest collaborations that's been around for a number of years is called Pan-STARRS, based out of Hawaii, or the telescopes in Hawaii mostly. And, they look for basically, like Rebecca said, things that are moving on the night sky night to night, or that appear out of nowhere on the night sky. And that's the exact same way that you find supernova, that you find new exploding stars. And so there's this interesting synergy between two very, very different fields of astronomy, what we call, they're sort of lumped under transient astronomy, where things that change with time is basically what that means. But you have people who are looking for new exploding stars, supernova, my research groups back at Berkeley and at UT and around the world. And they're using the same equipment, the same software, the same, way to try and find new objects in the night sky as the people that are looking for new asteroids or comets or things like that. And so the Neowise comet that came by just a few weeks ago is discovered using this kind of technique. Pan-STARRS is another term you might see in front of some of these comets, and that's looking for asteroids, comets, and supernovae, kind of all at the same time, using the same telescope, the same camera, and the same techniques and software to try and find that stuff.
Yeah, it's a big endeavor, and I'm very excited. And I think that's all of the questions that we have for everybody. So we're probably going to end the show there. I just wanted to give you guys all one more thank you for being here. You guys did a great job. Jeff, is nice to have you back. And stay tuned, everybody, for some of the things that he's got going on. Check out our Astronomy on Tap friends over at Bryan College Station and see Micah's talk earlier. And Jacqueline is at A&M. So, she's doing some cool stuff over there, and she's in talks there as well. So thank you to everyone for being here. Thank you for watching. We will say goodbye.
Thanks for joining, everybody. Have a good night.